Hello, my name is Spiro Karigiannis. I'm a member of the Department of Pure Mathematics at the University of Waterloo. I'd like to thank the organizers for asking me to give a talk in this asynchronous conference. Everything I'm going to say today is joint work with Darren Chang and Jesse Madnick at Waterloo and Taiwan. We're just in the process of finishing the writing of the paper. The mathematics is all complete, so I suspect the preprint will appear on the archive probably within 2 to 3 weeks. So by early April of 2022, you should be able to find our paper on the archive. So let's get started. Even though I know many of you know what calibrations are, I'm going to review it anyway, especially because I'm going to slightly weaken the definition of calibrations for our purposes. So here's the setup. We have an n-dimensional Riemannian manifold, and we have a smooth K-form on this manifold called alpha. Then we'll say alpha is a calibration if and only if, for every point in the manifold, if we plug in k orthonormal tangent vectors to M at that point, we get a real number that's less than or equal to 1. And of course, if we then replace one of these vectors by its negative, it follows that this is also greater than or equal to minus 1 for all k tuples of orthonormal tangent vectors. This, by the way, is not the usual definition of a calibration. This is what's usually called comass 1. And the usual definition of calibration is that it's a comass 1 form together with the fact that it's closed, d alpha equals 0. But I'm not going to assume that it's closed most of the time. Okay? So suppose we have a calibration, then we can define a distinguished class of oriented k-dimensional subspaces of each tangent space. So let's let LP be a k-dimensional subspace of the tangent space to M at the point P with a given orientation. And then we'll say that this oriented k-plane is calibrated with respect to alpha if and only if, whenever we put in an oriented orthonormal basis for LP, we actually achieve this maximum plus 1 on alpha. Right? So if we plug in an oriented orthonormal basis for L, we're going to get into alpha, we're going to get plus 1. That's what an oriented k-plane is. And then finally, we can define what it means for an oriented k-dimensional submanifold to be calibrated with respect to alpha. So if we have an oriented k-dimensional submanifold of M, we're going to say that it's calibrated with respect to alpha if each of its tangent spaces is calibrated with respect to alpha. Each of its tangent spaces is a k-dimensional subspace with an orientation because our submanifold is oriented. Okay? And we just defined in part 2 here what it means for each of these tangent spaces to be oriented. And it's easy to see that equivalent characterization of being oriented is that the restriction of alpha to the submanifold L is equal to the volume form. Now this makes sense because there's a metric on L obtained by restricting the metric from M to L, and we have an orientation on L, and therefore since we have a metric and an orientation, we get a volume form. So this form is well defined, and we know that any k-form on L will be some function times that volume form. And this condition here tells us that that function always has to be between minus 1 and 1. So alpha restricted to L is going to be a function in general, a function times the volume form, where this function takes values between minus 1 and 1, and we say that the submanifold is calibrated if that function is identically 1 on L. Okay? So that's the definition of a calibrated submanifold. Here's the fundamental theorem of calibrations if you've never seen it. This is due to Harvey and Lawson back in their pioneering paper in 1982 in Acta Mathematica. Here we're going to assume the calibration form is closed. If d alpha is 0, then whenever we have a compact calibrated submanifold of L, it's absolutely volume minimizing in its homology class. That means if we took any other submanifold, oriented submanifold representing the same homology class as L does, then its volume will be at least as large as the volume of L. Okay? In particular, since it's absolutely volume minimizing in its homology class, it's certainly locally volume minimizing, so it's certainly a critical point of the volume functional. And therefore, it must have zero mean curvature. So these calibrated submanifolds are a special class of minimal submanifolds. So a minimal submanifold is a second order condition, second order PDE, because the mean curvature is a second order invariant we get from the second fundamental form. But being calibrated is a first order condition. First order condition. Because it tells us something about the tangent vectors to the immersion. Okay? So this is the calibrated submanifolds are a special class of the minimal submanifolds. All right, so let me give you a proof of this fundamental theorem because it's so easy. It's really 3 lines. So what does it mean, first of all, for two submanifolds, two k-dimensional oriented submanifolds to represent the same class in homology? Well, that means that if we take the union of the two with the opposite orientation on one of them, so this means the union of L and L tilde, where we give L tilde the opposite orientation, then this is the boundary of some k plus 1 dimensional oriented submanifold. That's exactly what it means for them to represent the same homology class. And then we just compute, well, the volume of L is equal to the integral of its volume form, and the volume form is the same as alpha restricted to L because of the hypothesis that L is calibrated with respect to alpha. And then we can replace L here by L tilde plus the boundary of a boundary of W. And so that's what I've done in the second line. The integral over L is equal to the integral over L tilde plus the integral over the boundary of W. But on this term, I can use Stokes' theorem and write this as the integral over W of d alpha. And that's 0 because we're assuming alpha is closed. So this is crucial here that alpha is closed. So then the second term has vanished, and now we're integrating over L tilde, we're integrating alpha, and this is less than or equal to the volume form of L tilde for any L tilde because alpha is a calibration. Okay, so putting these all together, we get that the volume of L is less than or equal to the volume of L tilde, which is exactly what we wanted to show. Okay, so I'm going to emphasize again, this theorem is true when alpha is closed, right? Calibrated submanifolds are minimal and even better than minimal when the calibration form is closed. But the calibration form doesn't have to be closed to define this distinguished class of submanifolds. They just won't necessarily be minimal. Okay? So that's important because when I state our main theorems, they're going to be about calibrated submanifolds where the calibration form is not necessarily closed, and therefore these calibrated submanifolds are not necessarily minimal. Let's look at some examples, and in fact all the important examples that we're going to talk about in this talk. They're the following. So first of all, we can have an even dimensional Riemannian manifold with a metric and a compatible almost complex structure. That means J is an endomorphism of the tangent bundle that squares to minus the identity, and it's orthogonal with respect to the metric. This is an orthogonal almost complex structure. And then we get an associated Kähler form. Omega of uv is g of ju v. And because J is an orthogonal almost complex structure, omega is a 2 form. It's a 2 form on M. Okay? Doesn't have to be closed. And so that's not going to be necessarily my calibration form. I'm going to allow myself to take powers of this, and there's this normalization factor 1 over k factorial. So if I look at alpha, which is omega to the k over k factorial, this is a 2k form on M, and this is a calibration. This has comass 1. This is the classical Wirtinger inequality. Okay, so it follows from this Wirtinger inequality, in fact, that if I have a 2k dimensional oriented submanifold of this manifold, then it's calibrated with respect to this form if and only if it's what's called an almost complex submanifold. If J was an integrable complex structure, then this would be an honest complex submanifold, but I'm not assuming that J is integrable, and I'm not assuming that omega is closed. So J not necessarily integrable, and omega not necessarily closed. Okay, so that's the classical example of calibrations. What's another way of saying what this means? It means that J of the tangent spaces of L are contained in the tangent spaces of L. The tangent spaces of L are invariant under J. Okay, the next example is a 7-dimensional Riemannian manifold with a G2 structure. So there's a Riemannian metric, and there's a distinguished 3-form, a special kind of 3-form on it called a G2 structure. Many of you I know what those are. It doesn't really matter if you don't know it. You just have to take from this the fact that it's a special kind of 3-form with special algebraic properties at every point. And this 4-form psi is just the Hodge star of phi. So these are all oriented, and therefore since we have a metric and an orientation, we have a Hodge star, so we can define the Hodge star of phi, and this is called psi, which is the 4-form. And it turns out both phi and psi are calibrations. They have this Comas 1 condition. If I have a 3-dimensional oriented submanifold, it's called calibrated with respect to phi. It's calibrated with respect to phi. These are the so-called associative submanifolds of M. And the ones that are calibrated, the 4-dimensional oriented submanifolds, which are calibrated with respect to psi, are the so-called co-associative submanifolds of M. Okay, so if you know what those are, that's great, but you won't need to understand exactly what these look like in order to follow the rest of the talk. And then finally, case 3, which is very similar to case 2, is an 8-dimensional Riemannian manifold with what's called a spin 7 structure. So this is a special kind of 4-form. We don't get anything else here from the Hodge star because these are self-dual 4-form. Star of capital phi is capital phi. Okay, and in this case, the submanifold, so this is a calibration, and the submanifolds which are calibrated, the 4-dimensional oriented submanifolds which are calibrated with respect to phi, are called the Cayley submanifolds. Okay, so I'm going to state a theorem talking about all 4 of these cases. Okay, the theorem, I'll state it 4 times because in each case it'll be slightly different, even though it has the same flavor. Okay, so before we can state the theorem, let's look at the following setup. So we have an n-dimensional smooth manifold. Eventually we're going to put a Riemannian metric on here, but not yet. And let's fix an embedding of a compact oriented k-dimensional submanifold. So we have Lk embeds into Mn. This is compact and oriented, and this is an embedding. And we're not going to change this. This is going to be fixed throughout the discussion. What we're going to be interested in is, does the second fundamental form, does this embedding, this submanifold have special properties with respect to an ambient metric on the space M? So more specifically, more precisely, what do I mean? We're going to do the following. We're going to consider a functional where the input is a metric upstairs on M. We're going to input a metric on M, and we're going to output the volume of this submanifold with respect to the induced metric. So remember, we said L is oriented, and if I put a metric on M, by restriction that induces a metric on L, and therefore with the orientation I get a volume form. So I can integrate that volume form, and I get the volume of the submanifold with respect to the metric it gets induced from G. Okay, so this is very different from the usual construction of minimal submanifolds by looking at the volume functional where the thing that's varying is the immersion, right? The map from L into M. We're fixing this embedding of L into M, and we're varying the metric upstairs. Okay, that's the volume functional with a different input here. So if we have a path of Riemannian metrics upstairs in the ambient space with initial velocity at time 0 equal to h, this is just some symmetric 2 tensor on M, then it's easy to compute what is the first variation of this functional at time 0 for this path? And if you do the calculation, you get that it's equal to the integral over L of 1/2 times the trace on L of H. So H is a symmetric 2 tensor on M. We can pull it back by the inclusion to get a symmetric 2 tensor on L. And we have an induced metric on L. And we can compute the trace of that. So that means exactly this. It means the sum, it means the sum over, it means the sum from A equals 1 to K of H of EA, where E1 up to EK is an orthonormal basis. EK is an orthonormal frame for L. Okay, that's the trace. So that's just the first variation formula. And of course, whenever you have some functional and you can compute its first variation, it's natural to say, well, what are the critical points, right? Which metrics upstairs will be critical for this functional? And it's easy to see that if you just allow all possible variations of the metric upstairs, this will have no critical points. Because, for example, you can just take scalings of the metric upstairs, take the metric g and multiply it by e to the t. And then you're going to get something purely positive here, right? So this will never be 0 for such variations. Okay, but we can look at a special class of variations of the metric, and which excludes those, for example, and then ask, are there critical points in that case? So this is what we're going to do. So this is what I just said. If we allow arbitrary variations of the metric, then no metric is going to be critical for this functional. It has no critical points. But what we're going to do is the following. We're going to say, suppose our Riemannian manifold has a calibration form on it. Like these examples we saw of the associative, co-associative, Cayley, and Kähler calibrations. Then what we can do is we can look at a special subclass of variations of the ambient metric upstairs that are induced by varying the calibration form in a special way. So I'm going to say explicitly what I mean in all these 4 cases as we go along. But we're going to have a calibration form on this Riemannian manifold. We're going to vary the calibration form, and from that we're going to get a special type of variation of metrics upstairs. Okay, as I said, the more precise statement is coming. And then we're going to prove 2 theorems. Okay? Theorem A says, suppose that L is calibrated with respect to alpha. Right? So we have some initial metric g and a calibration alpha. And remember that the notion of being a calibration certainly depends on the metric, because it says something about putting in orthonormal tangent vectors. So suppose that L, which is fixed, that compact oriented embedding is fixed. Suppose that L is calibrated with respect to alpha, then the metric g is critical for all variations of this special form, which I haven't told you yet. I haven't told you what this special class of variations is, but we're going to get to that. And then theorem B is essentially the converse of theorem A. So we're saying suppose again the embedding is fixed of L, and we're saying suppose that the metric g is critical for variations of this special type that I haven't described. Then in fact that submanifold had to have been calibrated with respect to alpha. Right? So as I've stated them here, there really are exactly converses of each other. But I want to state them separately, especially because when we get to the spin 7 case, the story will be a little more complicated. But the other reason I wanted to state them separately is because, in fact, the way we prove theorem B is by picking a particular explicit member of this class of variations. Right? So we're going to pick one particular variation that lives in this class, and we're going to show that if it's just critical for that kind of variation, then it has to be calibrated, and therefore, since it's calibrated, by theorem A, it's critical for all variations of that special type. In other words, being critical with respect to variations of this special type is equivalent to just being critical with respect to one particular type of variation in that class. Okay, so that's where we're going. This is the introduction to the statement of the theorems, and now we're going to prove or I'm going to at least give you a sketch of the proof of these two theorems in 4 cases, okay? And this is a good place to stop and continue in the next video.